In this series LCR circuit, the switch S is closed at time t equals 0. The initial charge on the capacitor, Q at time 0, is written Q sub 0. The rate of change of the charge in the capacitor with respect to time at time 0 is 0. So what does that mean? Well, at time 0, the charge is Q sub 0. So I'm just showing what the graph of Q against T will look like, at least for early times. dq dt is 0 at time 0. So that means the slope of the graph at the point Q0 is 0. So the tangent to the graph will be a horizontal line. So the graph will start off like this. The charge will decrease. We want to show that Q as a function of time is given by this decaying function. So this term here indicates that Q of t is decreasing with time. We have no voltage source in this circuit. Alpha is a positive constant because alpha is the resistance divided by twice the inductance. So this will be a decaying exponential. By the way, we should have no t here. We just multiply the constant Q0 by e to the minus alpha t. For this circuit, solve it to find Q as a function of time. The charge in the capacitor is a function of time. So we are going to get the potential difference across each element in the circuit. So let's look at the potential difference across the inductor. Well, here we have the difference in potential between point A and point B. So we have the potential at A, V of A, minus the potential at B, V of B. So here we are assuming that the current is flowing in a clockwise direction. Of course, we could have it flowing the other way. So anyway, if we just take the current flowing in a clockwise direction and calculate VA minus VB, that's equal to the inductance of the inductor L times the rate of change of the current I with respect to time. Next we get VB minus VD, that's the potential difference for the resistor. Well, that's just the resistance of the resistor, capital R, times the current, little I. And finally we want the potential across the capacitor. That's the potential at D minus the potential at F. That's the charge on the capacitor, Q of T, which we're looking for, divided by the capacitance C of the capacitor. Now, we apply Kirchhoff's law. We want the potential difference across the entire circuit. That's the potential at A minus the potential at F. Well, we get that by adding up the three potential drops. So we want VA minus VF. You can see if we add these three together, the VB's cancel, the VD's cancel. And that must equal 0 because there is no voltage source in this circuit. There is no battery in this circuit or some other voltage source. Now, current is defined to be the amount of charge passing a point in the circuit in unit time, or dq dt. So using this we can get di dt. So we differentiate with respect to time. We differentiate dq dt with respect to time, and that's the second derivative of q with respect to time. So we get the sum of L di dt, Ri, and q over c, and we replace di dt with d2q dt2. Then we have R times I. Well, I is just dq dt, so we plug dq dt in for I, and finally we have q over c. So the dependent variable is q, the independent variable is t. So we have to solve for q as a function of time. L, R, and c are constants. Now, let's take the Laplace transform of the differential equation. Well, we can use the linearity property to take the operator L in through this equation. Since the inductance L, resistance R, and capacitance C are constants, we can pull those out. And on the right hand side we have the Laplace transform of 0, which is 0. Now, we need the Laplace transform of the second derivative. Well, we can just look that up. Here it is. So our function is little q of t. Next we plug in the initial conditions. Q at time 0 is written Q sub 0. That's the initial charge on the capacitor. goes in for q of 0, and dq dt at 0 is 0, so that term drops out. Next we need the Laplace transform of the first derivative, so we can just look that up. Here it is. So little f is little q in this case. Actually there's a misprint here. We want to get the Laplace transform of little f of t. In this case our function is little q of t. And as for little f of 0, we just want little q at 0. We write that as q sub 0. So we sub those into our differential equation, and we want to isolate L of little q of t. So factorizing it out, we have ls squared here, we have rs here, and we have 1 over c here. So that's in square brackets here, and we shift over minus l s q naught, and we shift over minus r q naught to the right hand side. Dividing across, then we get L of q of t. Now in the denominator we have a quadratic in S. We are going to complete the square of this quadratic. First of all, we factor L out of the denominator, and we get this here. We have an S here. The next step in completing the square is to get half the coefficient of S, and write our quadratic as L into S plus r over 2l. So half of r over l is r over 2l. We need to square this. Now let's see what we get if we square this. We get s squared plus this times this doubled. Well, that'll give us back r over l times s. And then we square the second term. That's going to give us r squared over 4l squared. So we need to subtract off this term, because we don't want that, and we need to add in this term 1 over LC. Now for r over 2l we are going to write alpha. So r and l are constants, so obviously alpha is a constant. Now this is r over 2l all squared, so this here is alpha squared. And for 1 over LC minus alpha squared, we will just write omega squared. So this is all a constant. So we just call this thing omega squared. So this is our new denominator, and we plug that in here. We split up the numerator. The numerator is ls plus r, well, times q naught actually. So all of this is multiplied by q naught. So we take ls over the common denominator, and we take r over the common denominator. So we just split this numerator, ls plus r. So we have two fractions now, and each of these fractions should look familiar. We took inverse transforms of these things before. So now we go and get L inverse of this here, and that'll give us L inverse of L of q of t, which is q of t, of course. Using linearity we can take out q0. That's just a constant. That's just the charge on the capacitor at time 0. Now if you go to your table of transforms, you won't see a function of this form in the tables. You'll see this here, s over s squared plus a constant squared. So this is quite close to it. If we can only replace s with s plus alpha and then use a shift theorem. So we put a plus alpha on top here. So now this fraction has the same form as s over s squared plus k squared, where s is shifted by an amount alpha, and we can use the first shift theorem to handle that. So we will be using this rule here. So if we plug in a alpha on top here, we're going to get another fraction, alpha over s plus alpha squared plus omega squared, and we need to cancel that out by writing minus alpha over s plus alpha squared plus omega squared. So the fractions with alpha as numerator will cancel out, and we will be left with s over s plus alpha squared plus omega squared. What about this fraction over here? Well, we use this rule here. We have a 1 on top, so we need to change that to omega, because the constant in the denominator is omega squared. Comparing to this, the constant is k squared, so we have to have the square root of it on top. So if we have omega squared underneath, we must have omega on top, so we can apply this rule here. But if we stick omega on top of this, we have to divide by omega. Now let's take the inverse transforms using linearity. Now, as I said earlier, we need to apply the shift theorem here. S is shifted by an amount alpha. So here's the shift theorem that we use. To get the inverse transform of big F of S plus A, which we're calling this thing, we have e to the minus a times t. Well, a is alpha in this case, and that's multiplied by little f of t, where little f of t is the inverse transform of big F of S. So big F of S is just this fraction with S plus alpha replaced with S. So we want inverse transform of S over S squared plus omega squared, and we saw that that's the cos of omega t. So that's this property here, with k replaced by omega. Let's look at the next fraction. Now, comparing to our rules here, we want something of this form here, constant on top, because alpha is a constant, and something of the form s squared plus a constant squared in the denominator. Well, that's what we have, except s has been shifted by alpha. This constant squared is omega squared, so that's omega is k, but we have to have omega on top, so we need to stick an omega on top here and then divide by omega. So this is what we're actually after. We need to take out omega, and then we can use linearity to take out minus alpha over omega. So we'll have minus alpha over omega times the inverse Laplace transform of this thing here, omega over s plus alpha squared plus omega squared. Next we use the shift theorem. We can see that s has been shifted by an amount alpha. It's got the same form as this, except s has been replaced with s plus alpha, and k is equal to omega. So we'll end up with sine omega t in our answer. That's what we have here, sine omega t. And of course we have this constant minus alpha over omega. But the shift theorem tells us we have to multiply that by e to the minus alpha t. See, we have e to the minus at, where a is the shift. Well, a is equal to alpha in this case. S is shifted by an amount alpha. Finally, we have this fraction here. Well, we can see that we use this rule here. It's got the form k over s squared plus k squared, where k is equal to omega. And s has been shifted by an amount alpha, so we need to use the shift theorem. So little f of t is the inverse transform of omega over s squared plus omega squared. So little f of t is sine of omega t. So that's what we have here, and we have the constant r over L omega taken out in front, and we have to multiply by e to the minus at, where a is the shift in s. So a is equal to alpha, so we have e to the minus alpha t. Now, finally, we sub these three expressions into this up here. We have to multiply by q0. So we see that e to the minus alpha t appears in all three of them, so we can factorize that out. We can also factorize sine omega t out of these two expressions. So e to the minus alpha t is factorized out of all of them, and the q0 is factorized out of all of them. We've cos omega t, and then we're left with minus alpha over omega here and r over L omega. Finally, we need to show that our solution can be written like this, where alpha equals r over 2l and omega squared is 1 over lc minus alpha squared. So we need to write the r over L term in terms of alpha. So if alpha equals r over 2l, if we multiply both sides by 2, we see that 2 alpha equals r over L. So we replace r over L in this term with 2 alpha. That's all we do, and we have a common denominator of omega, so we have 2 alpha minus 1 alpha, that's 1 alpha.